So the idea is now to see what is the consequence of what we have just seen. That is that the in case that we have open orbits, then the motion of the electron in the direct space can be thought to be along a specific direction. Now, the discussion is done using the same approach that we have used up to now. So you don't try to solve the full equations, you just try to use a qualitative approach to investigate what is the consequence of this result. So the idea is the following: if you suppose to have your sample, so you have your sample, you apply a magnetic field that is orthogonal to the plane of the sample, then you apply the electric field, and this is the field you want to use to, let's say, let the current flow through the sample. I use the same approach that is used in the textbook. So the direction of motion of the, let's say, the orbit along which, the direction of the orbit along which the electron may move into the solid is labeled as this versor n. So from now on, I will use versor n to represent the direction of one possible open orbit. Please, just to clear the thing, when I mean the direction of the open orbit, I do not mean in the reciprocal space, I mean in the direct space. So actually is n represents the direction that is rotated by 90 degrees with respect to the direction that you have in the reciprocal space. So n is a direction, is an orientation in the direct space. And in general, n is not said to be parallel to E. So let's say it may happen that the applied electric field is parallel to n, but that is not a general assumption. So we may suppose that the direction of n is not parallel to E. So I suppose that n is an arbitrary direction not parallel to E. What we have just learned is that when B goes to infinity, what happens? When B goes to infinity, the capability of the electron to move in the system is just along that direction. So this means that if you have a current in the system, and that current may propagate only along an orbit that is parallel to n. So in this situation, if you notice, in general, what you expect that if you apply an electric field parallel to E, the motion of the charge will be parallel to E. But in this case, the motion may not take place along this direction because the open orbits are along n. So something has to happen to prevent the electron to follow this trajectory, that is the trajectory of the open orbit, due to the fact that the electric field that you apply from the outside is not along n. And what happens? What in the Drude picture was the Hall field? If you remember in the Hall diagram that we draw when we consider the Hall effect in the Drude approximation, we had an electric field that was orthogonal to E. So in this case, the idea is a new field, that is the Hall field, develops so that the combination of these two fields give you an internal total field that is orthogonal to n. So that happens as the system tries to prevent the electron to follow the direction of n due to the fact that n is not the direction along which the current may propagate in the system, due to the fact that, again, you try to let the current flow along the direction of the external field, because in principle you may not know what is the direction of the open orbit. So you expect that the whole field develops, and in this case the development is due to prevent the electrons to follow this trajectory. And as E total is orthogonal to n, the direction, just to label that, orthogonal to n is called n prime. So n is the direction of the open orbit, n prime is the direction orthogonal to the direction of the open orbit. In this configuration, what may we say concerning the electric field? Oops. So the electric field, in principle, is not said to be or parallel or orthogonal to n, because when you apply the external field from the outside, in principle, you do not know what is the direction of the open orbit. So E is written as a combination of these two terms, and now I will comment on those. So E is a combination of one part that is parallel to n and one part that is orthogonal to n. So the second part is parallel to n prime. All the symbols that I will use from now on that have as a label 0 represent quantities that in the limit of b that grows to infinity will reach a constant value that is different from 0. All the quantities that from now on I will use that have a label that is 1 are quantities that in the limit of b that grows to infinity will go to 0. So what is the meaning of this representation? The meaning is, in principle, E is a combination of both components, one parallel to n and one orthogonal to n, depending on the electric field you apply from the outside. But since we know that the open orbit, that the trajectory of the electron develops along the open orbit only in the high field limit, what happens is that in the high field limit, the electric field may not be along the direction of the open orbit, because the direction of the open orbit that is represented by n is not along the direction where the current may flow in this sample. So due to that, the electric field, when b grows to infinity, may not be parallel to n, but has to be parallel to n prime. And why is that? Because if the electric field is orthogonal to n, so the electric field is orthogonal to the open orbit, then no current will flow along the open orbit, because you may consider that to be a sort of preferential direction of motion for the electrons. Or in other words, it's just like as if the system could propagate current only along that direction. If the electric field is orthogonal to that direction, then no current may flow in the system. In particular, no current may flow along that direction. And you require that as again, the direction of the external field, that means the direction along which you want the current to propagate, is not in this situation parallel to n. So this is a requirement, just a qualitative requirement concerning E. Then what happens to the current? The current in general is represented as conductivity times the electric field. So in this case, we write the same thing as we did before, but we have to say that the only conductivity term that survives is the conductivity term that is parallel to n, because n is the only direction that may propagate current in the system when we consider the high field limit. So in this condition, we have that sigma 0, and the convention is always the same. So all the terms that have a label with 0 are terms that in the high field limit will be constants, so different from 0. So this represents the contribution parallel to n and depends of the projection of the electric field along the direction of n. What we are missing then, what we have now is sigma 1e, where sigma 1 is anything else, so all the other possible contributions to the density current that depend on E, but while sigma 0 in the high field limit will be constant and different from 0, sigma 1 in the high field limit will be equal to 0. So the meaning of this equation is, in principle, the density current may flow along an arbitrary direction, both along n and also along another direction that is not parallel to n. But in the high field limit, the only direction that may be useful for the propagation of the current is the direction that is parallel to n. So the conduction along any arbitrary direction is suppressed, that is due to sigma 1, while the flow of current along n, the direction of the open orbit, is preserved and depends on sigma 0. So these two equations just, let's say, try to represent the fact that only the open orbit is able to let the current propagate through the system. So as a first step, let's try to find an expression of the density current that combines the equation of E for E and the equation for J. So we have that this is equal to sigma 0 n. Then we have scalar product of E0 n prime plus E1 n plus sigma 1 that is applied to E0 n prime plus E1 n. So we have sigma 0 n. Then in this equation, n is orthogonal to n prime. So only the terms with E1 survives. So we have E1 here. Then we have sigma 1 times E0 n prime. So sigma 1 applied to E0 n prime plus sigma 1 applied to E1 n. This can be approximated to sigma 0 and E1 plus, if you notice here, we have sigma 1 and E0. So something that goes to 0 when B grows and something that is constant. Here we have sigma 1, E1. Both terms go to 0 as B increases. So the leading one between these two is just the first, because we have one term that goes to 0 and one term that is different from 0 in the high field limit. So I just keep the first term of this equation. So sigma 1, E0, and then n. The idea of the calculation is to, I forgot to make that clear at the beginning of this part, is to focus on the magnetoresistance. So the question is, has the resistivity of the system any dependence on the magnetic field? So, or that is observed experimentally, but may we justify the fact that the resistivity has a dependence on the magnetic field? So in this case, the aim of the calculation is to find an expression for the resistivity and to understand whether that resistivity depends or not on the applied field. So if we want to express the resistivity, we have that E is equal to the resistivity times the density current. And if we write this expression as resistivity times the versor of the density current times the modulus of the density current, then to evaluate the resistivity, we may just multiply everything by the versor of the density current, and at the end we have that the resistivity is versor of the current times E divided by the modulus of J. Okay, so I just changed the page. So the final equation was the resistivity is equal to the E times the versor of the current divided by J, that is the modulus of the current density. In this case, the vector product, the scalar product between E and the versor of J leaves us just with E0 n prime divided by J modulus. So the point is to evaluate this term here now. So to evaluate n prime, we may start by evaluating just the scalar product between n prime and J. What we saw before is that n prime J is sigma 0. E1 plus sigma 1 E0 n prime. Yeah. So in this case, here we have n prime, here we have n, so this multiplication gives us 0. So what we have here is that this is equal to just n prime scalar product sigma 1 E0 n prime. And since E0 is just a number, so it's a coefficient, we may also, let's say, take this E0 in front of everything. So this is just E0 times n prime sigma 1 n prime. So if we write n prime scalar product J as n prime scalar product J versor times J modulus, we have, and we know that this is equal to E0 n prime sigma 1 n prime. Then we have that E0 divided by J modulus is equal to n prime scalar product J versor divided by n prime sigma 1 n prime. And we may substitute this into that equation. So we have that the resistivity is equal to n prime scalar product J versor squared divided by n prime sigma 1 n prime. What we have at the numerator is just a number that depends on the relative direction between these two versors. So this is just a number and doesn't depend on the magnetic field. At the denominator, we have again two versors, so those versors do not depend on the magnetic field. But what we know is that sigma 1 in the high field limit will go to 0. If sigma 1 goes to 0, this means that the resistivity is expected to increase. So this expression tells us that as the magnetic field increases, so as the open orbit becomes the only possible source of propagation for the current in the system, then we have that the resistivity of the system increases and in principle may go to infinity. Then when you actually measure the resistivity of the sample, you do not observe that the resistivity goes to infinity. You just notice that the resistivity increases. So what is found experimentally is just the increase, so nothing goes to infinity. But in this case, the increase is predicted by the fact that sigma 1 decreases as the magnetic field, as the intensity of the magnetic field is increased. So this is a sort of indication of the fact that again, the resistivity of a sample may change its value depending on the application of the magnetic field. And in this case, the value is expected to grow as the field is increased. And the growth is just due to the fact that, going back to the diagram that I showed you before, if the external field is applied along this direction and the direction of the open orbit is like this, as this is the only possible direction along which you may have a flow of current in the high field limit, then in the high field limit, no current will propagate along E, because the current may not propagate along this direction, but only along this direction. So the increase of resistivity is due to the fact that the open orbit is not along the main direction of application of the electric field. So let's say if we suppose, for instance, to make a diagram where we plot how the resistivity changes. So if we make a polar plot and we suppose that along this plot the possible directions for n are, this is just an example. So if this is the direction of n, and you plot here a line, so you plot resistivity for a specific value of B as a function of the orientation along which you apply the electric field, what you expect is that when the electric field is applied parallel to n, then the resistivity is low. And as the orientation changes, the resistivity increases. So I know that this is not a nice diagram, but is it clear at least the meaning of that diagram? The diagram is the polar plot representation of the resistivity measured for a fixed value of B. So this line here and also this line here is equal to the resistivity that you measure when the external electric field is applied along this direction. So if the direction is not the direction of the open orbit, you have a large value of the resistivity for a fixed value of B, where B is a large value. So you choose a large value of B. Differently, when the electric field is applied just parallel to the open orbit, then the flow of current can be observed very easily, and due to that, the resistivity of the system decreases. So if you make such plots for your system, you may find out what is the direction of the open orbits. In general, just to make a diagram that is more close to reality, since we need to consider the symmetry of the crystal, and if we consider, for instance, a cubic crystal, then we have that the system is invariant. So if this is an orientation of an open orbit, we expect that also the orthogonal one would be the orientation of the a possible orientation from the open orbit. Then what you expect to find is that here the resistivity is minimum, then the resistivity increases, then minimum, increases, minimum, increases, minimum, increases, minimum. So again, this is a plot of the resistivity of B when the electric field is applied along one direction here in the plane. So again, the distance between the origin and one point of this curve is proportional to the resistivity the resistivity that you measure along when the electric field is applied along this direction and when the value of the magnetic field is fixed but is large. So even if this is just a rough method to have an indication concerning the energy band structure of the system, just measuring the resistivity at different values for different value of the orientations of the electric field can give us an indication of the presence of open orbits. Because if we observe open orbits, we expect that along the open orbits, the resistivity will decrease. So we expect to find diagrams like this one here. Okay. Do you have questions or comments concerning this part? I know that the calculation is just qualitative, so no detailed calculation from the starting equation. But so the calculation is presented just to give an idea of what happens. So the important thing is that the general idea is that you have been able to understand the general idea. So is everything clear, or you have questions or comments?
I've got only one question. I didn't understood what's the difference between this graphic and the previous one.
In the first one, since in my initial diagram, just one possible direction was presented for the open orbit, I just made the diagram for one direction. So the first one was just the one corresponding to the diagram that I presented before. So the case where I made the drawing with the sample and just with one direction for n. But in this case, and that diagram corresponding to this situation. But in general, one needs to consider that the the crystal, the lattice has a symmetry, and so also the open orbits will follow that symmetry. So in general,
Oh,
I
okay.
would expect that this direction corresponds to another, for instance, orthogonal direction for another possible open orbit. So this is the diagram that should be closer to reality.
Okay, thanks.
Okay, so we may conclude this part just by saying that both the fact that the Hall coefficient could change from sign, so was found to be larger and smaller than 0 in the lab, can be now justified by the fact that in the evaluation of the Hall coefficient, we may in principle include both the contribution of electrons and the contribution of holes. So these two parts here that, let's say, are not always there, but maybe there in case you have different bands, and you consider that, for instance, the one band, the easier way is to consider the electron contribution, and for the other band, for instance, it's easier to consider the Hall contribution. So in this picture, you may justify the fact that the Hall coefficient may change sign depending on the system you are considering. And in this case, due to the fact that the electronic density that you have here and also the Hall density are not fixed at the beginning of the calculation, but are obtained as a result of the integral using the density of states in the reciprocal space, then this justifies the fact that the modulus of RH was different from the modulus that was predicted by the Rood model. So in this very simple representation, both the change in modulus and the change in sign can be explained somehow, making reference to the electronic band structure of the system. So we somehow reconciled the experimental results with what is expected by using the configuration where we have block electrons and the semi-classical equation motion. Then concerning resistivity, now we have the opportunity to predict resistivity dependence on the magnetic field. So in this case, this resistivity dependence is expected to be such that the resistivity goes to infinity as the intensity of the external field increases. In general, in the experiment, you do not see actually an infinite value for the resistivity. You just see that the resistivity increases its value as the magnetic field is increased. So also this phenomenon is predicted by the application of the semi-classical equation of motion to specific systems, in particular to systems where we have the opportunity to observe open orbits, where open orbit means an orbit that is able to span different Brillouin zones depending on the value of the relaxation time. So you always expect to have relaxation time large enough to be so to allow the electron to move through at least more than one zone, and then you also expect to have a magnetic field large enough such that only the open orbit is the orbit that is able to transport current within the system. So both conclusions, the one concerning RH and the one concerning the magnetoresistance, are now in agreement with the expectation that are found applying the semi-classical equations of motion. So at this point, somehow the two questions that were there from the beginning of these lessons have somehow found an answer. So the answer is if we consider the modified version of the electronic band structure, that means the version that we have after the Bloch theorem, and if we consider also systems with open orbits, then we may consider both effects. In general, if you do, let's say, if you do not have open orbits, at least you may be sure that the Hall coefficient is now closer to the experimental value, and in principle you do not expect to observe a magnetoresistance that increases depending on the value of the external field. So even in a qualitative way, it's now possible to conclude that the part that was started just from the beginning of the solid-state physics lessons. And the last thing I would like to present you regarding the application of the semi-classical equation of motion is an equivalent, something that resembles what we did when we considered the Sommerfeld model, and that is the let's say, evaluation of the conductivity in case we consider Bloch electrons. So in this case, the idea is to find an expression for the conductivity just when, as we did with the Sommerfeld electrons, just when the external electric field is applied to the system. So also in this configuration, we may use, let's say, a way of evaluating the conductivity that is similar to the one that I presented to you in that situation. I use a slightly different approach that resembles the approach of the textbook. And also in this case, the approach is based on the use of the distribution function. I don't remember. In that case, I used F for the out of equilibrium distribution function and F0 for the equilibrium one. So if so at the equilibrium, we have F0, okay, and that may in principle depend both on the position, on the wave vector. I assume that at the equilibrium, there is no time dependence. So we have a situation that is fixed and doesn't depend explicitly on the time coordinate. When we are out of equilibrium, we may have an F value that depends on the position, on K, and also on time, depending on what is happening to the system. So if we just consider, and let's say, what are the contributions that influence F of R, K, T? The contributions are external forces, and in this case, we may use the semi-classical equations to include the contribution of the external forces, and then we have collisions. So as we did in that case, we need to consider both contributions regarding the evolution of F. Then if we consider only external forces, then if we consider F let's say F gives us the number of electrons per unit volume that are found corresponding to position R, wave vector K, and time T. So if we want to obtain the actual number of electrons that are found in that position, that wave vector, and that the amount of time, we have to multiply F by the volume element in the space, in the direct space, and in the reciprocal space. If, let's say, if we just follow the contribution of the dynamics, so no collisions, just the contribution of the external forces, we may use the equation of motion to find the evolution of R. And if one particle now is in position R, this means that at time, if we move in the past using a small variation of time that is dt, the electron that was initially in position R, if we consider not time t, but t minus dt, was in minus v times dt. So the position, if we go back in time by an amount equal to dt, can be predicted by the equation of motion. So concerning the position, we use minus v dt to go back in time. Concerning the wave vector, we use k minus k prime dt. Then we have t minus dt, and then the volume. I use t minus dt just to say that is the volume in the phase space corresponding to t minus dt. And then I have d3k t minus dt. Since in this equation we just consider the contribution of dynamics, this is the phase space volume that corresponds to time t, and this is the phase space volume that corresponds to time t minus dt. So two different volumes corresponding to two different instants in the time evolution. But if the time evolution is just due to external forces, so due to the dynamics of the system, there is the Liouville theorem that tells us that the volume in phase space, so this volume here and this volume here, is the same and may be simplified, since classical equations preserve the volume in the phase space. So at this point, we may simplify those two parts here. So we are left with the fact that the value of f at time t is equal to the value of so these two values are the same. At this point, we may expand this second term here and make an expansion at the first order with respect to the coordinates r, k, t. So this is equal to f of r, k, t minus the derivative of f with respect, the gradient of f with respect to the position times the variation. And the variation is v times dt. The minus sign in front is due to the minus sign. So this minus sign here is the equivalent of this minus sign here. Then I have minus the gradient with respect to k of f r k t k prime dt, and then I have minus the derivative, partial derivative of f just with respect to time times dt. This is the so this is what I expect just if classical dynamics has to be considered. So in the variation between f at time t and f at time t minus dt, this should be the leading equation. And as you note, this term here can be simplified with this term here So we are left with the fact that the sum of these three terms has to be equal to 0. So this, if we only consider external forces. If we add collisions, we have that F at time rkt is equal to F is, let's say, here we just pick up this equation, so the initial equation that we obtained before. At this point, we may to include the fact that from time t minus dt to time t, some of the electrons undergo a collision. So at this point, we may lose some electrons, and we may also obtain some new electrons in the, so in this case, we have the contribution of collisions. And regarding the contribution of collisions, I just now write what is that contribution. We observed that the contribution of collisions is equal to F. So the number of electrons. So if we have the electrons in this configuration, then the electrons in that configuration have a probability that is proportional to dt to undergo a collision, dt divided by the relaxation time. And in this case, we have a minus sign in front since we are losing electrons. Then the problem was to evaluate the, let's say, contribution of all the other electrons that suffer a collision in some place, at some values of k, and then appear in the rkt position. What we saw is that this additional contribution can be expressed as F0 rkt dt divided by the relaxation time. And this is due to the fact that collisions contribute and maintain the system at the equilibrium. So this means that if we are at equilibrium, then so if the collisions maintain the system at the equilibrium, this means that the equilibrium distribution function has not to be modified by collisions. So the contribution of collisions at the equilibrium is, using the same approach that I used before, is minus F0 rkt. So this has to be equal to 0 because no deviation of F0 should be observed if we have F0 as a distribution function. So the only way to make this summation equal to 0 is to sum f0 r kt dt divided by relaxation time. So the idea is, if at the equilibrium the distribution function may not change, then here we have a term that is similar to this one here. So we use the actual distribution function with a minus sign in front times dt divided by relaxation time. And in the equilibrium case, we have to add exactly the same thing to keep things at the equilibrium. Now, in this situation, the situation we are evaluating, we are out of equilibrium and we need to estimate the second term. But if we exploit another feature of the collisions, that is that the effect of collisions is to erase any contribution of the external forces. So any contribution of the, let's say, F distribution function is cancelled by the collisions, then we are justified to use this term here in both situations. So both in the equilibrium configuration, and in that case we had to use that term to keep things to 0, and also in this new configuration where we are out of equilibrium. And we may use here the equilibrium function by remembering the fact that the collisions erase any effect of the external forces. So to estimate the contribution of collisions, we may refer again, also in this case, to the equilibrium distribution function and not to the out of equilibrium distribution function. So that's why we have these two terms, minus the out of equilibrium distribution function and the equilibrium distribution function. Okay, so the approach is exactly the same approach that we used before, but in this case, yeah, we recall the same features of the collisions. So they keep the system at equilibrium, and if we are out of equilibrium, they try to bring back the system to the equilibrium. So that's why we use F0 here. If we now combine the two things, we have that 0 is equal to minus the gradient of r with respect to r of f r k t times velocity times dt minus the gradient with respect to k of f r k t k primes times dt minus the derivative of f with respect to t of r k t, and then we have the contribution of n times dt, and then the contribution of collisions, that is dt divided by the relaxation time times f r k t minus f0 r k t. At this point, we may divide everything by dt, we may simplify dt, and we may take these three terms on the other side of the equation. So we have the gradient of with respect to r of f times scalar product velocity plus the gradient with respect to k of f scalar product k prime plus the derivative of f with respect to t is equal to minus 1 divided by the relaxation time f r k t minus f0 r k t. At this point, I will use the same approximations that I used in the previous calculation, that is no spatial dependence. So the electric field is uniform. If that is uniform, then the gradient with respect to R of F is equal to 0 because no position dependence in the distribution function. Then we also have, we're supposed to be in stationary conditions. Stationary means whatever the shape of the out of equilibrium distribution function, that shape will not change with time. So we have the explicit derivative of t, sorry, of f with respect to t is equal to 0. So due to those hypotheses, this term here disappears and this term here disappears. So we are only left with the gradient of f with respect to k on the left side. On the other side, we have the usual collision term that is f out of equilibrium minus f0 at the equilibrium divided by the relaxation time. Okay, so, and this is the final point that is quite close to the final point of the calculation that I obtained during the previous calculation. So now it's 11:30. So I think I will stop here. I will go on with the calculation tomorrow morning. So please just keep in mind this equation that is quite close to the previous equation. What will change from now on is the derivative of k, since now we have to use semi-classical equations to evaluate the derivative of k, and this will produce the, let's say, a slight difference on the final solution with respect to the result that we found for the Sommerfeld case. Okay, if you now, yeah, so I will go on tomorrow with the calculation.